So we're going to finish up our model comparisons. We'll do our application exercise for that. And then we're going to do two short little lectures, one on how to actually select predictors now that we know kind of what the model comparison tools are. And then finally, I'm going to go through the conditions for for multiple linear regression, because I've had kind of several questions about this based on the homework, and I think hopefully this will sort of help. And I'm also going to show you a couple other techniques you can use when some of those conditions are violated. So we've talked a lot about how to check those conditions, and we've talked a little bit about what to do if they're violated, but this is going to go into a little more depth on that. And then finally, for the lab today, that's going to be an opportunity to actually examine how to apply these techniques when you're just sort of handed a data set and asked to fit the best prediction model possible. And so for that, you're going to be using that same data you just used in the homework. If you noticed in the homework, all three of the models that I proposed were pretty bad fits to the data. They all violated some assumption. So whether it be the linearity assumption or the constant variance assumption or the normality assumption, I actually think all three of the models violated all three of those. And so what you're going to do in the lab today is see if you can find a model that does not violate those assumptions. And once you sort of determine maybe the subset of models that don't violate those assumptions, see if you can then pick the best prediction model among them. And so that's going to be what we do for the final part. All right, so picking up where we left off for the model comparisons, we left off at the kind of starting this application exercise. And so if you want to go ahead and find this, you can pull this into RStudio Pro by copying this link from GitHub to get the template files. For this, we're going to be fitting a model to predict college GPA in the first year of students using their high school GPA and some other variables. So the first model, I want you to use high school GPA and their verbal SAT score. For the second model, I want you to use high school GPA, their verbal SAT score, and their math SAT score. For the third model, I want you to use high school GPA, verbal SAT score, math SAT score, and the number of humanities credits taken. So you'll have models 1, 2, and 3. And then I want you to compare these using nested F-tests. And then finally, also compare these three models using either AIC or BIC to rank them. So spend a couple minutes working on that, and then we will do it together. All right. All right, so I am going to go ahead and load our data. We're using this first year GPA data. If I wanted to fit that first model as specified, what would I do? Yeah. All right. And so that's going to be my first model. I can look at what that looks like just in general. It looks like that explains about 25 or so % of the variability in GPA when I look at the high school GPA and the verbal score for the SAT. Great, so that was model 1. What would I do for fitting model 2? Yeah. Yeah, so now I would have high school GPA, SAT verbal, and which one are we adding here? Yeah, SAT for math. All right, and I can look at a summary of this. Oops. And looking at this, it suggests to me that it doesn't look like adding that SAT math really adds much to our multiple R squared. It doesn't look like we really add much by adding that, but we can also look at the F test to try to assess that in just a minute. And also we could compare our adjusted R-squared. So our adjusted R-squared for the model without SAT math was 0.239, and with it's 0.235. So that suggests that it went down when we added that variable, which suggested basically that the penalty that we've incurred by adding additional variable was sufficient to outweigh the amount of variation that variable explained. So sort of suggests that probably this SATM is really not adding a lot of information to this model, which kind of makes sense. We're going to talk about this in a couple minutes, but what might be happening here is that the verbal score and the math score, perhaps these are highly correlated, or perhaps they're kind of the combination of these is highly correlated, and so we're not really adding much information by adding this in addition. All right, so that's that. Now, let's fit that third model. What's going to go into my third model? Yeah, exactly. So it's the same thing plus this number of humanities credits taken. And so this looks like, that looks like it's better than my previous two. It explains about 30% of the variation. My adjusted R-squared is also higher than the previous two were. But we can look at an ANOVA or use an F-test to be able to assess that a little bit more carefully. So let's do that now. The first one I wanted you to do was do an F-test between Model 1 and Model 2. So if I wanted to do that, what code would I use?
Question. So because the last Model 3 was the highest R-squared, do you know that necessarily that would be higher if you took out SAT math? Because the second one was lower than the first one?
Yeah, that's a great question. And actually, last class when we did this, we fit a Model 4. So we can do that too. That's a really good question. Let's fit a fourth model to add into the mix here that looks at high school GPA, SAT verbal, and humanities. And we'll leave out that SAT math because it looked like adding that wasn't really helping us. Yeah, it's a good question. So let's look at that. And we can also, we can compare that R-squared here to the one previously. So it looks like this is pretty close to what we saw before, which probably would be what you would expect since we didn't see that the SAT math was adding that much information. The adjusted R-squared with SAT math was 0.296, and the adjusted R-squared without is 0.298, so a little bit higher. So that would suggest that this Model 4 is probably going to end up being our favorite. And I'll swap the question to look at this Model 4 instead, because I think that probably will be more informative as well, or maybe in addition rather than instead. But let's first look at an ANOVA just between 1 and 2 to try to see kind of if what we thought we saw via R-squared holds true when we do our F-test as well. So how would I do an F-test looking at the difference between Model 1 and Model 2? Yeah, ANOVA, Model 1, Model 2. Oops. Gotta spell ANOVA right. There we go. So is Model 1 nested within Model 2? It is, because the variables in Model 1 are contained in Model 2. And so this is necessary if we're using an F-test to compare these two. They have to be nested, and that holds here, so we're good to go. What is the null hypothesis that this particular F-test is testing? It's the beta associated with SATM. So that would be, it would be beta 3, but the ordering kind of depends on how you put them into the model. But basically the null is that the beta associated with this SATM variable is equal to 0. And so then what's the alternative? It's not equal to 0, exactly. And based on the output in this table, what's the result of that hypothesis test? Right, Right, exactly. We failed to reject the null because this p-value is greater than that alpha 0.05 that we usually use as our cutoff. And how do you interpret this p-value in the context of this test?
Probability of getting a f value that f statistical value that's equal to or greater than the one we calculated here.
Exactly.
Given the null hypothesis is true.
Given the null hypothesis is true. Exactly. So the probability of getting we saw an f statistic of 0.1166. The probability of seeing one that was this or greater, given that the null is true, so given that the true beta coefficient for SATM is 0, would be 0.73. So we have a 73% chance of seeing a f statistic like this, given that the null is true. So knowing that that was our hypothesis test, looking at is there another, I'm going to show you the summary of Model 2 output. Is there another hypothesis test, or is there like another p-value on this output for when I just looked at Model 2 that is testing the same hypothesis as that f-test?
One across from SATM.
Exactly, this one across from SATM. So we end up with the same p-value here because this is testing the exact same null. This p-value is associated with this t-value, which is testing the null hypothesis that the beta coefficient for this SATM is equal to 0. And so this is the same reason why in simple linear regression, the f-test is exactly the same as that 1t test for beta 1. And it turns out just in general, if you're just adding a single variable to the model, so here the only difference between these two models is the second one includes SATM. It turns out that the f-test for that, the null is going to be exactly the same as the t-test for that particular variable in the bigger model. And so you don't actually need to look at you wouldn't need to look at this analysis of variance table. You can get all the information you need by just looking at this value here. You can similarly use, so we know that if we squared our t statistic, we would get our f statistic. So we basically would learn everything we need by just using this table here if we wanted to in this particular case. Okay, I'm going to now, instead of comparing, which model do you think would be preferred based on the results of this test? Model 1, exactly, because it looks like Model 2 is not significantly better. So if we were sort of aiming for parsimony, meaning we're sort of aiming at fitting the minimally best model we can, it looks like Model 1 kind of is sufficient. So I'm going to now compare Model 1 to Model 3. And now is Model 1 nested within Model 3 here? Yes, it is, because the two variables in Model 1 are also in Model 3. And what is the null hypothesis for this f-test now? Exactly, that beta hat 3 and 4 are equal to 0, so that these two betas are equal to 0. And so now, because we have two that we're adding, we can't just look at if we just look at the summary for Model 3, none of these t-tests correspond exactly to this test, because now we're looking at this combined test of two beta coefficients. And so we can't use that to sort of as a shortcut for what we would get here. We really do need to do an f-test here. So the null is that both of these are equal to 0, that the coefficients for both of these are equal to 0, and the alternative is that at least one is not equal to 0. And so based on that, what is the result of this f-test? We reject the null, exactly. So this p-value is really tiny. It's something way less than, it's like 0.00008. So way less than that 0.05 cutoff. So that suggests that the bigger model is significantly better than the smaller model. Now, as you rightly pointed out, this bigger model includes two variables, one of which we've sort of already shown is maybe a little bit redundant. So maybe that Model 4 would really be a better comparator for Model 1. So let's try that, or rather for Model 3, since we've just deemed Model 3 better, we can compare Model 4 to Model 3. The reason I'm putting Model 4 first here is because it's the smaller model, so you always put the smaller model first when you do these. It will still work if you put the bigger model first. It's just gonna, here, I'll show you what happens if we do if we swapped it, it would be fine. It would just give you this negative sum of squares and this negative degrees of freedom, which is like sometimes a little bit harder to conceptualize. So I like to always put my smaller one first. All right, so what's the result of this? What's the null hypothesis for this test? Exactly, the beta for this SATM is equal to 0. And what's the result of this test? We fail to reject the null. And so based on this, would Model 4 or Model 3 be preferred? Model 4, yeah. And what would be a shortcut if I didn't want to run this ANOVA and I just wanted to use the output from Model 3? Is there a way I could do that to get this, to test this same null hypothesis?
Check the summary to see the t-test.
Exactly, I could check the summary and look at the t-test, and that's going to test that same hypothesis here. So this 0.484 is exactly the same as this 0.484 here. And similarly, this 0.4915 is just the square of this t-statistic. So these are testing the same thing. All right, so this is telling me that Model 4 is the best model of the ones that we looked at based on these f-tests. Now, using kind of p-values as our way of assessing which model to fit, this is something that is a little bit, it's becoming a little bit out of vogue in statistics these days. And that's because significance testing is driven by your sample size. So if you have a larger and larger sample size, you're more and more likely to see kind of significant results, even if the actual magnitude of those results is very small. And I think you can kind of get some sense of why this would be when you think about the relationship between this F statistic and the T statistic, because the T statistic divides by the standard error. And that standard error has a square root of n in it. It's just the standard deviation divided by the square root of n. So as n gets bigger and bigger and bigger, the standard deviation is necessarily going to get smaller, which says nothing about the actual estimate of the beta coefficient. So you can detect smaller and smaller differences from the null as your sample size gets bigger. So for example, like this, for example here, we're testing whether the beta coefficient for SATV is equal to 0. This value is pretty close to 0, but because the standard error is so small, the p-value ends up being also very small, and therefore we end up getting a significant result. And so kind of the utility of p-values for trying to assess which model best fits your data, it becomes less and less useful kind of as you have more and more observations and fewer variables. So that's why methods like AIC, BIC, and adjusted R-squared are sometimes preferred for picking predictors, which is what we're going to do in a minute. So, okay, so speaking of AIC and BIC, if I wanted to compare these four models using AIC, what function would I use? Yeah, AIC model 1. And I can also do AIC model 2, AIC model 3, and AIC model 4. All right, let's run these four. Which one is the best based on AIC? Model 4, we know that because it's the smallest, and so smaller AIC is better. And what's the next best? Model 3, and then which one's next? Model 1, and then Model 2, exactly. So AIC, turns out, agreed with what we saw from our F-test, which also suggested that Model 4 was the best. If I wanted to use BIC, which is just a, yeah.
Can you explain what AIC is again?
Yeah, so AIC is basically, so there's this, it is a measure of goodness of fit, so how well your model fits your data, your actual data that you're observing. that penalizes a little bit for the number of variables in your model. And so the method by which it uses, the thing it uses to tell if it's this thing called log likelihood, which if you go on with stats, you'll definitely learn about what that means kind of from a statistical standpoint. But basically, from what you need to know for this class is that these models, they assume some distributions, and the log likelihood basically says, okay, you assumed these distributions with these variables. How close were you to what the data points actually were? And then you can use the summary metric to sort of say how far off you were, and then it penalizes a little bit for adding extra variables. And that penalty is important. We'll see it in just a second. But if you didn't include that penalty, then basically the more and more variables you included in a given sample, the better your model would look like it fit, just because you would be essentially overfitting to that data set. So it's a metric that kind of gets at both the goodness of fit, which means how well the data fit what the model that you picked is, that penalizes a little bit for the number of variables. BIC is the same. It also uses the log likelihood as the way that it determines how well your model fit, and then it also penalizes a little more than AIC. So BIC is going to it's always going to kind of give a stronger penalty for the number of predictors included. A lot of times AIC and BIC will agree. The times they don't agree, it's usually when there's a pretty close call between models. So based on this, which model was the best for BIC? Yeah, 4 as well. It turns out BIC here picks exactly the same ordering, 4, 3, 1, and then 2. All right. Let's switch to the next one. So now we're going to talk a little bit about how to actually select predictors. Okay, so selecting variables. So when the goal is inference, what do I mean by inference? What metric am I often, or what statistical quantity am I often interested in if I'm answering an inferential problem, or if I'm doing inference based on my model? So the way you can tell I'm asking an inference question is often if I ask you a question about the beta coefficient. So the beta coefficient is sort of summarizing the relationship between x and y. If that's the quantity I care about, that coefficient itself, or equivalently, if I care about the t statistic associated with that coefficient, or the p-value associated with that coefficient, or the confidence interval associated with that coefficient, then I'm trying to answer an inference question, because ultimately I'm trying to understand the relationship between x and y. So anytime you're trying to understand relationships, it's when you have inference as kind of your goal. When you're trying to understand the theoretical relationship between some explanatory variable and some outcome variable, you need to adjust for confounders. So that was we had that example, the extreme example of Simpson's paradox, where you needed to adjust for the department. I think our example, we were looking at the proportion that were admitted to one of the UC schools, and we had it broken down by gender, but it turned out there was this confounder department that was really important that we needed to adjust for. So anytime you're trying to understand some relationship between some explanatory variable and an outcome variable, and you're trying to actually quantify the impact of that, and especially when you're trying to quantify the causal relationship, so how much of some outcome y is caused by the explanatory variable x, you need to adjust for all the confounders, which would be any variables that are kind of on the causal pathway for x and y. And so it turns out that there's not actually a statistical test that you can do to assess whether you've included all relevant confounders or all relevant variables when the goal is inference. And that's because just because two variables are correlated doesn't necessarily mean that they're causal. I think that's one thing I think that we sort of know pretty well from this correlation is not causation type issue. But that's why there's not a good statistical test to be able to assess whether you have all the confounders, because a variable could be correlated with X. It also could be correlated with Y, but depending on where it falls in the pathway, it may not be a confounder, and so it may or may not need to be in your model. But that mechanism would need to be determined based on some additional knowledge. Some information like the timing of the variables would be important. So for example, if you had some explanatory variable and then subsequently had a variable that it was intermediate between that explanatory variable and the outcome variable, so it's sort of the X variable, your explanatory variable causes this middle variable, which then causes the outcome variable. This is an example of sometimes people call this mediation. This would not be a confounder. And so you wouldn't want to adjust for that variable in your model. But if all you did was look at the correlation between X and that variable and Y in that variable, you would see that they were correlated. So this is sort of a really long-winded way of saying that when your goal is inference, you're reliant a little bit on expertise about the data generating mechanism when you're trying to figure out which variables to include. And so often you have to rely on pre-specifying these models based on content matter experts who would tell you what things need to go in those models. And you might do a whole lot of sensitivity tests to see basically how your betas might change kind of in the presence or absence of certain variables in your model. So kind of like how when we were trying to see influential observations, we either removed the observation or put it into the model, and then we saw how that changed our beta coefficients. Similarly, we could do types of analyses where we add or subtract variables from our model and we see how much it changes our beta coefficients. But if we wanted to know which one of those coefficients was actually correct, we'd have to know what the data generation mechanism was. So this is all, I feel like I've got a very long-winded way of saying that when inference is the goal, there's really not a statistical mechanism that you can use to determine what should go in your model. You sort of need to rely on having some information a priori. So most of what I'm going to talk about now for selecting variables is going to be in the space of prediction models, where we actually can use some of the tools that we've done so far. So when the goal is prediction, so that means we're interested in predicting a new Y variable, or if we're interested in basically building a model that explains the mechanism between X and Y, or that can a bunch of X's and Y, we can use the metrics that we learned about last class to basically compare models and pick one that has the best metrics there. So there's a little bit of a dance here trying to decide what to put in the model to begin with, and I'm going to talk a little bit about some considerations there, although some of that too is going to be some trial and error or just brute forcing and trying a whole bunch of different predictors. But I'll talk about some things that I think about when I'm trying to decide what predictors to assess. And so the first thing that sometimes comes to mind is, what if we just look at every combination of all available variables? So if you had 10 variables in your data set, maybe you could just look at the 1,024 different potential models that could be fit with those 10 variables. That is going to get intractable as the number of variables gets bigger and bigger, but it is one choice to be able to do. But one issue that you could run into here is this issue of multicollinearities. So one concern with including every potential combination of all variables is that we might include variables that are highly correlated. And why would that be bad? Well, in the extreme case, if one predictor has an exact linear relationship with one or more other predictors in the model, it turns out that you can't actually fit that. The least squares process doesn't have a unique solution. And that's because it won't know whether to attribute the variability explained to this variable with the exact linear relationship or the other variables in the model. So because there's not just one unique solution, you won't be able to actually fit a model in that case. And so here I've just simulated a little bit of data to sort of demonstrate what I mean by that. I have 3 variables here. The first 2 are generated from a normal distribution. This 100 here just indicates that I'm generating 100 variables, so my sample size here is 100. So I have 100 observations for x1, 100 for x2, and then x3 is equal to this linear combination of x1 and x2. So x3 is equal to exactly x1 times 3 plus x2 times 4. And so if I try to fit the linear model using all 3 of these variables, our will complain. It gives me this NA value for x3, and that's because it's not actually possible to fit the model like as I've specified here, because x3 is a perfect linear combination of the other two. So R is smart enough to know that it shouldn't try to fit that model. It's just going to drop that coefficient from your model altogether. But it does, you do have to sort of be a little bit mindful when you're fitting your models that this is going to be impossible. This is also why when we were creating those indicator variables ourselves and we included all of the indicator variables instead of like the k-1 categories of the categorical variable, we got an NA for that last one because that last one was a perfect linear combination of the rest of them. So that's the extreme case, that you could end up with predictors that are exact linear combinations. In the less extreme case, you could have variables that are not perfect linear combinations but still highly correlated. The downside here is that this could impact your variance. Now, what you might note here is I was talking about prediction, but now I'm kind of moving back into the inference space because I'm talking about standard errors. And this is a little bit of a dance here because if this variable truly was associated with both x and y, such that it was a confounder, you would need to include it even if it's going to inflate your variance. And so this is just sort of something to be aware of, but not necessarily, it doesn't always mean that you shouldn't include that variable. But in this case, it turns out I actually shouldn't because I have a variable x, a variable x2. x3 is highly correlated with x2, so x3 is equal to 4 times x2. It's not a perfect linear relationship because I've got this little bit of random noise here, but the correlation is quite high. And y is only equal to x1 plus x2, so x3 shouldn't actually be in my model. And when I include it in my model here, when I have x3, you'll notice it results in my standard error for x2 being quite large. So my standard error ends up being this 3.88, which is very big. And it also messes up my point estimate here for that as well, meaning that it's basically, this is supposed to be 1. So I generated this data, so I know that the coefficient for x1 and x2 should both be 1, but it's not here because I'm including this highly correlated variable that's kind of skewing my results a little bit. Whereas when I drop that variable, that highly correlated variable, I end up with a standard error back where it should be, around 0.1, and I end up with my significant p-value again. So multicollinearity, if you're not sure about, if you're trying to do inference and you're really not sure about your variables, which ones you should be including highly correlated ones can kind of mess up your results if they really are not truly confounders. Here I'm focusing on beta hat and its standard error. So is this a inference focus or a prediction focus? So this is a little tricky because I was talking about prediction up until this point, but because I'm focusing on these beta hats and standard errors, when I'm looking at these actual values, I'm concerned with inference. Prediction is like when I'm kind of looking at the combination of all of these and maybe trying to look at metrics like R squared and adjusted R squared to look at the overall, how well these models perform. But when I'm looking at the actual coefficients themselves, that often means I'm interested in prediction. So here, so far, I've described one case where perfect collinearity is not possible because it's actually just not possible to fit your model. It can be a bit of a problem with inference, particularly if you aren't sure that the variable that's highly correlated is a confounder, in which case it probably shouldn't be in your model anyways. But for prediction, we care about it if we're trying to fit a parsimonious model, which basically means if I'm trying to fit the smallest model that also has a good fit, if I have two variables that are highly correlated, or actually it doesn't need to be just correlated with one other variable, if it's highly correlated with the combination of all the other variables, then it's probably not going to add a lot of information to my model. So if some variable is highly correlated with everything else in my model, then maybe I could get away with not actually including that model in the prediction model itself. And so to determine how correlated a predictor is with all the other variables included, you can look at something known as the variance inflation factor, which is just equal to 1 over 1 minus r squared, where this r squared is not the r squared overall from the full model predicting y, but rather from a model predicting x, so predicting a particular explanatory variable from all the remaining predictors. So basically you look at, for example, here, if I was getting the variance inflation factor for x1, I would predict x1 using x2 and 3. So this model had, the full model had x1, 2, and 3 in it. I was predicting y. To get the variance inflation factor for one of them, I would put it on the right side of the equation and the remaining variables on the left. And I would look at the r squared value. The variance inflation factor is going to be 1 over 1 minus that r squared value. And so here, x1 has a pretty low variance inflation factor. This is very close to 1, which suggests that it is not highly correlated with either x2 or x3. So it's probably adding some additional information that those two do not contain. However, when I do the same thing with x2 and I get the variance inflation factor for x2, I end up with a huge r squared, pretty close to 1. It's 0.9993. When I look at that, 1 over 1 minus 0.9993, which is the variance inflation factor, I get this number that's over 1,000. It's 1,428. This is huge. As a rule of thumb, we usually consider, we suspect multicollinearity if the variance inflation factor is over 5. So basically that would mean if the r squared is over 0.8. And so this would suggest that either x2 or x3, if I'm doing a prediction model, I can probably drop one of those from the model because they're not really adding extra information. So this variance inflation factor can help us think about basically that we could maybe drop one of the highly correlated predictors from our model, and we would likely get a really similar answer, so that variable is probably not adding much to it. Okay, so that's one thing when we're trying to choose predictors. A first step could be just to see how correlated the different variables are and try to determine whether any of them are highly correlated, in which case maybe you could drop that one. But after that, what do we do next? Well, we could try every combination of all remaining variables. This is possible, but could get computationally expensive. So, for example, if you had 10 predictors, you'd have to fit over 1,000 models if you were choosing all the different ones. So it gets a little bit intractable. And another issue with trying every combination of model is that you could overfit your model to your data depending on the metrics that you're using to decide whether your model is good. And so that means that basically the model fit, it might fit very well to these particular observations, but it would do a poor job predicting a new sample. And so this is the danger. Often when we call this sometimes in statistics this bias variance trade-off. And so if you fit a model that really fits your sample data very well, sometimes we refer to that as reducing bias because you don't have a lot of bias in your actual sample. The difference between what you've observed and the model you're fitting is going to be small, but the variance is going to be larger because you're sort of overfitting to this particular data set. So this is like bias variance trade-off. If you take a statistical learning class, or actually some of our other higher level classes in our major, you'll learn a lot about this concept. We're just going to cover this very quickly here to sort of get an idea of what I mean by it. I've generated some data. It's not terribly important that you kind of know exactly what's going on, except that here I've got a whole bunch of random normal variables, x1 to x15. Y is only actually predicted from x1. The rest of these are just noise variables. And I've generated 2 samples from the same distributions. So both of these samples, they're basically 2 draws from the same population. And then I fit my model here to the first sample. And when I include 15 variables, I end up with this really high R squared of 0.67. So it explains 65 rather. These variables explain about 65% of the variability in this data. Although you'll notice my adjusted R squared is negative, so that's very small. That suggests that perhaps this is not a good model once we've actually penalized for the number of variables. But if I just used this multiple R squared, I might be misled into thinking that this is a pretty good model. And I could look at my residuals, and they look pretty good. There's not really an indicator just in that I've kind of overfit my model. But if I get some new data from that same population, so the mean of my mean squared error, the mean of my residuals squared in my original model was like 0.47. But if I get a new data set from the same exact distribution as my old one, and I try to fit my model there, these are the residuals that I get, which end up with a mean squared error of close to 12, so much larger than what I saw in my original data. And that's because that first model was really overfit. So it was sort of, I had a lot of variables relative to the number of observations. So it looked like my model was fit quite well, but it really wasn't. And when I got a new data set that was from the exact same population, it didn't fit well at all. And just to sort of show what that would look like, here those blue points are the residuals from my original data set, and the black points are the residuals when I tried to refit it on my new data. And this shows that basically the residuals are much larger on my new data, suggesting that that original data, the model was pretty overfit to that data. So the solution to overfitting, what you would learn kind of, the way that we handle this generally in statistics, is that you would fit your model on part of the data, and then you would calculate the error on the remaining part. So you would essentially split your data such that you train it, or you decide what predictors to include by fitting the model on a subset of the data, and then calculating your error on the part that wasn't in the initial training data. So this sort of separation allows you to save yourself from this potential for overfitting, because the data points that were not included in that original training data can't influence which variables end up getting selected. So this is sometimes referred to as cross-validation. Basically, it means you fit the model on a subset of observations and see how it performs on the rest. Then you average, you do this many times and average it across the whole data set. There's a special case of cross-validation called leave one out cross-validation, which means that you fit the model on n-1 observations, and so on all your observations except one. And then you see how it performs on the nth, so on the final one that wasn't in the original data. And then you do this many, many, many times, dropping one at a time, and then average your results. And then you pick the model that has the minimum error within your test sample. So I'm going to show you how to do this, but we actually won't need to do any of this in the class because some of our metrics have nice analogous meaning to these types of methods. But just to sort of show you both why this is going to be useful to understand and also why we want to make sure we only choose metrics to use that follow that use these kind of conventions. So here I've taken my sample and I've sampled 19. There were 20 data points in the sample. I've taken 19 of them, and that's my training data. And then I've created my test data as just the one observation that's not included in my training data. And I'm going to fit my really big model with 15 observations on that training data. If I look at the output from this model, it's got a very nice R squared here of 0.96, so I almost am perfectly predicting, so it looks like that's really quite high. My mean squared error is like 0.05, so this looks great for this model on the training data. But then when I test it on the one observation that I left out, I end up with a mean squared error of 19. And so this suggests that this model, while it looks like really good on the training data, is actually not that great of a model because it's probably overfit to those particular observations. And so I can do this. This was including all 15 variables. I could do this maybe dropping one variable at a time so you could see kind of what that looks like. And so here I've plotted with the first 7 variables. The blue line is the training error. And so as you would expect, that's going to go down a little bit as I'm adding more variables. I'm getting kind of more and more overfit to my data, so that error is going to decrease. Whereas the red line shows my test error, which means that because in this particular case, the truth is that I should only include x1, as I'm adding more variables, I'm doing worse and worse in my left out test sample. And so the way you would look at this graph is you would pick the smallest point using the red line, the test data, and so that would suggest that I just would want to fit a model with just x1. That's going to be the one that minimizes my test error that does the best. Okay, so that's all the kind of stat theory, but it turns out because in this class we're so far just using linear regression, you don't have to code up leave one out cross-validation. One of the reasons I taught you about AIC is that this metric actually mimics the choice from leave one out cross-validation. So it penalizes the model in the limit. So in kind of asymptotically, it penalizes it exactly like leave one out cross-validation would. And so it's going to also pick the right model without kind of being overfit. And so if I calculate AIC on those same 7 models, the ones that include X1 all the way up to this final model includes 7 variables. If looking at this plot, if knowing that the AIC value is on the y-axis, which model is the best? So for AIC, is it better to be bigger or smaller? Smaller, exactly. So the one that has the smallest AIC is going to be this first one, which would be the model that just has X1. So that would be the best one here, which is the same one that I got when I did leave one out cross-validation. So what this is saying is that we can use AIC. Basically, we can look at a whole bunch of different models and compare them using this AIC metric, and that should give us in the limit, that should give us the same result as what we would get if we were to actually perform this little bit more complicated leave one out cross-validation method. BIC is equivalent to leave K out cross-validation, where K is basically this function of N for linear models. And so it also has this nice property, which means we can use this metric also without having to code up the complex cross-validation as well. And in this case, it agrees with the AIC that it picks that first model as well. So what this is, all this is saying, the big picture here, is that for inference, we need to use our theoretical understanding of the relationship between our variables to properly select what to include in our model. For prediction, we can kind of iterate a little more. We could choose a set of predictors to assess, and as long as we pick a metric that balances parsimony with goodness of fit, so something like R-squared adjusted, AIC, or BIC, to select our model, we should be good to go. And so the best practice in general, kind of for any prediction model that you're building, is to fit the model on one set of data and test it on another. So using something like leave one out cross-validation. But it turns out for linear regression, AIC and BIC actually mimic this process, and so we can reliably use these methods without having to actually split our data. All right. Are there any questions about that before we move on to thinking a little bit about conditions for multiple linear regression? All right, so evaluating linear regression models. So I put together this little table that I was hoping you could use to kind of help put it all in one place, what we've talked about so far in terms of conditions for multiple linear regression. And so here the first assumption is linearity, and what that means is basically the relationship between the outcome variable and the explanatory variable or predictor is linear, holding all of the variables constant. So essentially that the functional form that you've included in your model accurately describes the functional form of the data. So how can we check this? We can use the residuals versus fits plot, which is what you did in the homework. Basically, you want that plot to be this like random cloud around that 0 line. And if there's not a pattern to it, then that would suggest that your linearity assumption holds. But if there is a pattern, and this is what we're going to cover today, if there is a pattern, the question then becomes which variable is driving that pattern. And that's where something, this marginal effects plot can come into play. This can help us try to decide which variable might be driving the nonlinear relationship. And so how could you fix this? Well, you could fit a better model, and by that I mean we could do transformations, we could add polynomial terms, or we could add more or different variables to our model. So this first one, transformations, we've talked about transforming our explanatory variable, as in like including kind of cubic or quadratic terms, but we haven't actually talked about transformations in our outcome variable, and this is actually another tool that you should kind of have in your tool belt when you're trying to fit models, because it can help with those assumptions. So it's common to transform the outcome variable by either taking the log or the square root of the outcome, and this is particularly useful for constant variance violations. So when you see variations in constant variance, one solution can be to either take the log or the square root of the outcome, and sometimes that can help. One note of caution is you have to be careful when you're interpreting coefficients after taking transformations, because now the transformation needs to be accounted for. So beta hat, for example, would be a 1 unit change in x, yields an expected change in the log of y if you took the log of the outcome, or if you took the square root of y before fitting your model, you would need to say beta hat is a 1 unit change in x, yields an expected change in the square root of y. So you would need to take it into account when you're analyzing your outcome or explaining your beta coefficients. Okay, so I mentioned these marginal effects plots. And so when we did simple linear regression, we could examine a scatter plot of x and y, but it's harder to think about how to do this when we have multiple explanatory variables in our model. And so one option is we could predict new values of y hat over a particular range of the x variable, and we could hold all the other variables at their reference values for categorical variables, or at their average values for continuous variables, and this might help us try to understand the relationship that we might be missing if we have some kind of nonlinear relationship. And so here is a residuals versus fits plot that might look familiar because it looks a little bit like the one you all saw in your homework. And so here, we actually have two violations here. It looks like there's some nonlinearity, and it also looks like there's some non-constant variance. And so from this residuals versus fits plot, I can tell that there's nonlinearity, but it doesn't actually tell me which variable is driving that nonlinearity. And so what you might do is you could fit these marginal effects plots for each of the variables you included in the model, and that might help you determine which variable you would need to adjust for in order to get to a better model. And so here, what I've done is I have created some new data. This plot on the right is looking at a marginal effects plot for the caret variable. And so I've sequenced from 0.1 to 3.4 by 0.1. So what that does is it just creates a vector that goes like 0.1, 0.2, 0.3, all the way to 3.4. The way I chose these values is I just looked at the range of caret in my data set, and I picked values across that range. And then I set depth to just the average depth in my data set, and I set color equal to the referent category D. And so then I plot my scatter plot of caret by total price, and I use that geom point to make the scatter plot. But then I add a line that includes this new data, and so now this on the x-axis I'm using this sequence from 0.1 to 3.4, and then on the y-axis I'm putting my predicted values, so I'm taking my model and I'm predicting using this new data. And what that shows me is this is basically my fitted line across these observed data points. And so what this kind of tells me is that it gives me some sense of kind of how this fitted line fits to this particular data, suggesting that perhaps I need to have that this caret variable might be the problem here when I'm seeing some nonlinear relationship. Perhaps I need to include something that accounts for that in my model. I did the same thing here for depth. So instead of looking across different values of caret, I set caret to just its average value. And then I sequenced depth from 58 to 79, since that was the range of depth. And I did the same thing here where the x-axis has depth, the y-axis has total price. And then I drew a line that was my prediction line. Now here, nonlinearity doesn't look like as much of a problem. It does look like we have some kind of latent classes here. So it looks like there's some kind of third variable that's dictating whether or not you have a depth between like 59 and 65, or maybe if you have a depth between like 68 and 80 or so. So it looks like there's some clustering that's not being accounted for by the model, but it doesn't look like this is necessarily a nonlinear relationship. So this would potentially suggest that there's some third variable that we need to be including, but not necessarily that we need to think about nonlinearity there. Okay, so based on that first marginal effects plot, I decided to add a squared term here to my model. And when I made my marginal effects plot on using this new model, I see that it much better fits my data. And if I looked at a residuals versus fits plot, I also would see that that nonlinearity assumption was no longer violated. Okay, so that's linearity. We test it using residuals versus fits. If there are violations, we might look at some marginal effects plots to try to decide where the violations are coming from. The way we would fix it is via either transforming y or adding polynomial terms or different variables to our model. The next assumption is zero mean, which is just that the error distribution is centered at 0. This is true by default, so we don't actually have to fix it. It will always be true. The next is constant variance, which that is just that the variability of the errors is the same for all values of the predictor. Again, we use the residuals versus fits. The way we fix it is by fitting a better model, and most of the time you can try to fix this by either taking the log or the square root of the outcome. So let's look at that real quick. Here I'm predicting the number of doctors in a metro region based on the number of hospitals. And so I built this model, this linear prediction model, and I plotted my residuals versus fits plot. Is the constant variance assumption met here? Yeah, it doesn't look like it so well to me because it looks like we've got kind of the variances and like the spread of these points over here looks kind of tighter. And then as you move across these fitted values, it looks like it fans out a little bit. It looks wider to me. So this looks like a violation of constant variance. And so the first thing I'm going to try is to take the log of the outcome. How does this look now? Better, yeah, this looks better to me for sure. It looks like maybe we almost have the inverse problem where there's like a little more variation here and maybe a little less down here. But overall, this looks much, much better than this one where there was kind of some clear fanning. We definitely have a little bit of like clustering over here, potentially due to there being some discretization in the data. So like these are whole numbers, which sometimes results in like values, a lot of places have the exact same value, which can cause this little bit of clumping. But this definitely looks better than what we were seeing before. How would you interpret this beta hat 1 in the context of this model where I took the log of my outcome? It's almost right. The only difference is now you would say for every one additional hospital, the expected change in the log number of MDs is going to be 0.1449. So now it's not just dictating the number of MDs, but rather on the log scale, the number of MDs. So when you make these transformations, you need to make sure that the beta coefficients are interpreted with those in mind. I could also try to take the square root of the outcome variable. How do you think this plot looks? To me, it looks a little bit better maybe because so here we looked like maybe our variance was getting a little tighter, so we moved across. Here it looks like a little bit more constant. Maybe this little more of just sort of a cloud, not so much of a pattern. We still have a little bit of this clustering down here, but this looks a lot better to me. So either the log or the square root. Maybe I would go with the square root if I were trying to fix the constant variance in this case. And so again, this beta hat 1 is going to be interpreted as for every one additional hospital, we expect that the square root of the number of MDs increases by 2.9. All right, so the next assumption is independence. And so this is that the errors are assumed to be independent from one another. It's not really checkable. It's just based on kind of understanding the data generation. And the way you handle this is either to find some independent data to help answer your question, so find different data, or to fit a fancier model. If you take STA 214, you'll learn how to fit models that can handle non-independence. So a little plug for, as you're registering for classes, to think about taking 214. It's offered next semester, and Dr. Evans is great. So that would be one to consider. And the next is randomness. This is basically the data obtained using a random process. Again, this has to do with the data generation. If you had deterministic data, then maybe you really don't need statistics because there's a deterministic relationship between your variables. But if you really were interested in trying to understand some kind of random process, then maybe you need to find some different data. And finally, the last assumption is that the errors follow a normal distribution. And the way that you test that is by looking at a QQ plot or a histogram of the residuals. If it's not true, so if that assumption is violated, often that means you just need to fit a better model, which means either transformations, adding polynomial terms, or adding more or different variables. Okay, so that is all we have. We've got about 10 minutes to start on the lab, and I'll give you some time on Tuesday to work on it as well to make sure you have time to ask questions. But what we're doing today, as I mentioned, is we're going to use that same diamonds data set that you used for the homework. But now I want you to basically, you can use any of the variables available in this data set that make sense in the context of a prediction model. I want you to try to predict the diamond's price using characteristics about it. And I want you to so the first step is going to be to find a subset of models that meet the assumptions of multiple regression. So basically try to find models that are that meet that constant variance, linearity, and normality, those assumptions based on those plots. And once you've kind of tweaked your models to figure out what you need to do to make sure that those assumptions are met, see if kind of within that subset of models you can pick the best one determined by the metrics we've used so far. So in the end, I want you to list all of the models that you've attempted. I want you to include the visualizations for the final model you pick. So you're probably going to iterate through a lot of different models, but I want to make sure in your report that you have that residuals versus fits plot and the QQ plot for the final model you pick, just to show that it met the assumptions of multiple linear regression. I want you to include the equation for the final model you fit. You'll likely use either AIC or BIC, or maybe adjusted R-squared to decide on the final model. So I want you to report the goodness of fit metric for that model and how it compared to the other models you tried. And then finally, I want you to use this new data set that I've put here to predict what a particular diamond with these specifications would cost, along with the appropriate confidence interval for that. And note, it's not a problem if you don't include all of these variables that I have in this new data in your model. This is just giving you all of them in case you decide to. So some things to consider. You might want to try transformations of the outcome. You might want to include polynomial terms to account for nonlinearity, and or you might want to check for interaction terms. Also make sure to carefully understand what each of the available variables in the data set means. So there's at least one in there that wouldn't make sense as a predictor. For example, if there is a variable that's a function of the outcome variable, then that would not make sense necessarily to include as a predictor, so just be mindful of that as well. Are there any questions about that? All right, so you can pull this in from GitHub and go ahead and get started and let me know if you have any questions.